Let's begin by talking about the lab and what you should have. Your data looks, I hope, something like this. You had a piece of paper and you would have had a line that looks like this, which represents the ball striking the ground without a collision. We're using this to represent the initial momentum of the ball before the collision. However, and this is why I hope you have a picture of it, you have a range where you actually hit, right? So a circle, and you chose the middle and drew this arrow to the middle of that range. And this represented the point just below where your object struck the ground. Then you had a bunch of strikes on one side. You drew a circle and you drew a line to that. And you had a bunch of strikes on the other side. And you drew a circle. And you drew a line to the middle of that. So you should have something that looks like this. You needed to measure this length, which we'll say is going to be used to figure out the velocity to the left and the velocity to the right. But this represents the initial velocity of the ball before the collision. This all look like what you guys did on Friday? All right, so our goal is to demonstrate conservation of momentum. The reason you need a picture of this is, although you took these measurements, I know many of you have like a drawing like this. How big would you say the circle was, this way and this way? Now, you have reference because you have a photo, but I'd probably say that the size of the circle was probably relatively the same for all three of those. You might have had some variance, but it should have been about like this. Now, as I walked around, some of you, your data came out bad. And I noticed this because, first, you didn't put the ball on the tee. And there's supposed to be a tee there. So some of your data was just a head-on collision, and all you've got was garbage. You needed a real collision where one ball glanced off the other, so they went in clearly opposite directions. Does that make sense? Otherwise, the data is garbage. You need to measure this angle and this angle. And you got to turn the volume off so that... Good luck. I believe in you. So here's what I want you to do. You want to show that the momentum before the collision was equal to the momentum after the collision. But you probably didn't take the mass of the ball. But can we agree that the mass of the ball was the same all around? If you were using the black plastic balls, both plastic balls had the same mass. And if you were using the silver balls, they had the same mass. And if you were using the clear balls, they had the same mass. So you're going to be looking at mv0 being equal to mvl plus mvr. But these are vectors. Because they're vectors, you can't just compare them this way. You'll have to break this up into the x direction and the y direction. However, if done correctly, if this is the x direction and this is the y direction, then the momentum before the collision in the x direction should be 0. And you want to compare mvl in the x direction with mvr in the x direction. And you want to do something similar in the y direction. Except this time you'll have mv0 in the y direction should be equal to mvl in the y direction plus m. Somebody moved something. Moved it all over the place. Stop moving stuff back there, whoever you are. I can't undo it now. Making me crazy. If you can't play along with my rules, you don't get to be on. You messed it all up. And I don't know who you are. Because I wasn't watching. There. Don't touch. Just leave it on the screen. So, anyways, I got to rewrite all that. MVR in the x direction, MV naught in the y direction equals MVL in the y direction plus MVR in the y direction. There you go. So all that really means is you taking each one of these vectors and finding out the size of the y component and the size of the x component, and doing something similar for this side. This is why you measured the angle and you measured the length of the vector, so you could find the two components. And you're going to be comparing these components. You'll notice that the m cancels out. So we really only have to compare the velocities, and that'll be sufficient. However, you're going to do one thing more than this. And it's not much, but you want to have a way of knowing whether you've gotten it or not. To demonstrate that momentum is conserved, these statements need to be shown to be true. They're not going to be perfect because you have a whole bunch of strikes and you actually don't know which pair went with which one. You just have a whole bunch of dents on the ground. So you don't know that this dent right here went with this dent right there. Do you understand what I mean by that? You just have a whole bunch of strikes from at least 5 different collisions. So these values have to be within an approvable error. So you need to measure the length in the x direction of your circle and the length in the y direction of your circle. Because that means this whole thing is plus or minus whatever the half of that size is. So if you find that length, say the x size of that circle, 1/2 of the size of that circle, the diameter, is your plus or minus error amount. You need to convert that into a plus or minus velocity. And you need to do that for each of these. So there'll be a plus or minus in the x direction and a plus or minus in the y direction. Hopefully your group is a circle and you can just find one diameter. But if yours is kind of oblong, then your width might be greater than your height. Does that make sense? I have 2 or 3 static examples that I left from Friday so that you can go and look at what you would have to measure. Now, you don't have to do this for every one of them unless you've got a group that looks really weird. So like if you have one where they were all like this and the rest, I mean, that's going to be really weird. But you might need to be careful about that one. But most of them end up being about the same every time. So if you measure it once, your plus or minuses, you can apply that across the board for all of your collisions. But you want to show if this is true within your margin of error. So this is going to be VL in the y direction plus or minus whatever your error is. That's the actual value there. Plus VR in the y direction plus or minus your error. And you want to see if that equals V naught in the y direction plus or minus its error. So it's pretty straightforward what I want you to do. I will see 3 of these based on your measurements. One for the 3 different trials that you did. Your write-up should be an explanation of conservation momentum. you should have in your notes us discussing it, beginning with Newton's third law and deriving from Newton's third law through impulse that the change in momentum on one object has to be equal and opposite to the change in momentum on the other. We derived this in class. So your theoretical discussion should be the derivation of conservation of momentum, which will end with P1 final plus P1 plus P2 final equals P1 initial plus P2 initial. Remember we went through this in class. This was first semester, but it should still be in your notes. If not, I just did it in second period. You can always just look at those videos where I do it. It really takes like 5 lines. It's not very much, but that's what I'd like to see. Then I want you to discuss your lab setup and how you collect your data. That should be short. But then for your calculations, there's no graphs or anything. It's just these calculations. Show me your data by maybe drawing a little picture and show me what your values were, and then show me your calculations, your sines and cosines and all of that to get the velocities. Probably something in there about how you calculated the time it took the ball to fall, maybe something on the root of t equals square root of 2h over g, something like that. And then just show me whether you were in spec or out of spec. Did you show conservation of momentum within your amount of error? If you did, great. If you didn't, say so. Some of your pictures, you weren't able to show it. I saw it as you took your data. Nope, probably not. That's okay. Your goal here isn't to prove that conservation momentum exists. It does. There's a lot of reasons why you might not be able to show it. So what you have to do is say whether your data demonstrates it or not. That's what I'm always looking for at the end of the lab. I scroll to the very end and look at what your conclusion is. Your conclusion is you saying something about your data set that answers what the purpose was. The purpose was to demonstrate conservation of momentum. If you don't demonstrate it, you don't demonstrate it. That's okay. That's what you're supposed to do, is interpret your data correctly, not force your data to show it. So I understand the difference here. If you don't show it, then you should say, I didn't show it. And that's fine. In fact, that's exactly what I would expect you to be able to do. What I really don't want is to have somebody turn in a lab where they didn't show it and say they did. That means you don't understand the concept. Now, this one's not hard to do once you have your data. If you did not take data because you were gone on Friday, and that's a big group of you, please come in after school and take a set of data so you can see how it was done. You can use your group's other sets. Just take one set so you can see how it's done. Does that make sense? It takes, you guys who did it, a minute or two to get set up, but then, less than a second to collect a piece of data. So it's not particularly hard. You may have stumbled through it a couple times. A few groups were a little dysfunctional, but it wasn't terrible. So it's not too much. We're about to go into a new unit, and it's rotational motion and dynamics. It is everything we did in first semester, but for things that spin. So all the things that were part of first semester are going to be here. And at the end of this, we will be combining all the stuff from spinning and all the stuff from translational motion into dealing with objects that roll. So the things that you have already done are going to come back here, and we're going to be seeing them again. We're going to talk about the kinematics of rotation, which means how things accelerate, how their velocity changes. All the stuff that we did in kinematics will come back here. I used to skip that part, but what I have found is that students really can't skip that. They need to go through it. So we're going to go through it. And I thought we could save a week by skipping it, but we're not. We're going to spend some time with rotational kinematics. It's just mind-numbingly dull, in my opinion, but you, I think, need to have that time. And then we will do the same things in the same order. We're going to do the same kind of discussion about how does something get started moving. And instead of unbalanced force, we're going to have something that causes unbalanced rotational motion. And then we'll derive stuff about rotational energy and rotational momentum. All of those concepts are going to be about things that are spinning. And at the same time, we're going to have things that are linked together, things that roll or things that move and spin at the same time. So students tend to find this to be a challenging unit, and it will make up and be about most of the time that we spend in third quarter will be on this. My goal is to finish all of the unit by the end of February and probably break the unit up into 2, possibly 3 tests. I'm going to be very upfront with you. The math here is in most cases not much more difficult than what you've already done, except for one piece that we have to be trained on how to do, and that's the calculation of something called moment of inertia. And we won't get to that this week. We'll get to it next week. But hear me out for just a moment. Nobody in the room, even if they've gone through BC, will know how to do this. But it does involve calculus. So although you may feel as though because you don't have calculus that you're going to be at a disadvantage, for the most part, you're in the same boat as everybody here. The difference is those people who have had calculus at least are not scared of seeing the symbology that's going to be used. But I want you to understand from the beginning, the hardest math of the year will be in calculating moment of inertia. And it is the least likely thing to show up on the exam. So although it may show up, and I want you to be proficient, if it shows up, they're going to give you the answer anyways. Go on, do the rest of the problem, and if you have time, you'll go back and do it. If you don't, you won't. But it also brings up something that you've never heard of before called the right-hand rule. And so we're going to talk about rotation from just a simple standpoint for a few minutes. That's out of the way. I'm not going to spend a whole bunch of time with that. I want you to think about the fact that the wheel was spinning just a moment ago. And I want you to consider what that probably means for what we already know. In translational kinematics, that's going to be the word I'm going to use now, translational. This dealt with objects that were changing location. We had a whole group and a whole vocabulary of things to describe an object that changed location. We had displacement, initial velocity, final velocity, acceleration, and time. We did some work in uniform circular motion, so you guys are aware that we can have rotational speed. And we described and talked about rotational velocity for quite a while. So this isn't coming out of nowhere, but for everything that has a translational component, there could be a rotational component. So an object that changes the direction it faces changes by a certain amount of radians or degrees. Angular displacement. So although these are both displacements, delta x and delta theta refer to one object changing its location or an object changing the direction it faces, its orientation. So you can imagine I'm going to have something for each one of these. For example, we've already talked about this. The Greek letter omega, lowercase omega, is used for angular velocity. So we'll say angular or rotational velocity. Different than translational velocity, and that describes the rate at which something's spinning, the rate at which its direction is changing. We'll use lowercase Greek letter alpha, which just looks like a fancy A, to describe acceleration and, of course, time. Now, I don't really think I have to derive this for you, so I think it's not unreasonable for me to expect you guys to think that if there was a translational equation that described how an object's position changed, that there would probably be a rotational one to describe how its direction changed. Can you see the simile here? So I'm just translating it. Can you see that translation? Is that okay? Can you do that 4 more times? If you can't, I will, so that you have all of them. But it shouldn't be too much to suggest you guys could know all of the rotational motion equations if you know all the translational ones. For example, Right, these are the two basic ones, the ones we get directly from calculus 2. And then we have all the derivative ones. All good so far? Any questions about any of that? All right. Let's see. I'm just going to stick these in the corner. You and your friends go to Busch Gardens and you ride the merry-go-round. Okay. One of your friends stands here. Each horse is 1 meter away from the other horse. So that would be 1 meter. That would be 2 meters. And that would be 3 meters. We all good to go? Everybody understand the basics? All right, we'll see. The ride begins from rest. And when spinning at full speed, you, the person standing right here, you see your friends pass you once every 4 seconds. Okay? The ride starts from rest, but when traveling at full speed, you see your friends pass you once every 4 seconds. It takes 10 seconds for the ride to get up to full speed. How many rotations did your friends make getting up to full speed? And what was the angular acceleration of the merry-go-round? Okay? I'll say it all over again. Starting from rest, your friends get on a merry-go-round and it begins to spin up. When at full speed, it takes 4 seconds for your friends to pass you and come back around. It took 10 seconds for the ride to get to full speed. How many rotations did it make getting up to full speed? And what was the angular acceleration of the ride? Now, we've done these problems before, but they are more convoluted because of the way the information can be presented to you. So let's talk about the information I gave you and what you don't have by just doing straightforward motion problems. I'm writing out the kinematics variables. I'm going to write in what we know. It started from rest. It's a good place to go. It takes 10 seconds to get up to speed. Now, we know that in order to do any rotational motion problem, you have to be given 3 pieces of information. So a third piece of information was given. What piece was that? 1 spin is 4 seconds. So my final angular velocity is 1 rotation every 4 seconds. And that's all it was given. Now, here's the thing. You have equations that can be used now to figure out any of the missing variables. The problem for us is units, I think, for the most part. I asked for rotations here. I didn't specify the units for this one. Right? So, work the problem out in rotations. You can leave it in rotations. In the same way, if the whole problem is in centimeters, you could leave it in centimeters. Or if the whole problem is in feet, you could leave it in feet. But work the problem out, but then I'm going to throw in some wrinkles. Okay, take a minute. So let's just do the easy one. The simplest one is to do the angular acceleration. Right? These four things would have to be used. Top equation. So I would just start by saying, all right, omega equals alpha t plus omega naught. So 1/4 equals alpha times 10. So alpha is going to be 1/40. And that would be rotations per second squared. Okay? Not too terrible. All right. I want to keep going. I'm supposed to find how many rotations did the ride make getting to this speed. I'm probably going to use omega squared minus omega. No, not that one. Why would I use that one? That's silly, Mr. Shelton, because you have time. So you want delta theta equals 1/2 times omega plus omega naught times t. That makes more sense. So 1/2 times 1/4 plus 0 times 10. 1/2 of 1/4 is 1/8. So 10/8 or 5/2. 5/4. Let's do math, Mr. Shelton. 5/4. So it looks like it makes 1.25 rotations. Not terrible. So we can add to this. How fast were each of the people going when the ride was at full speed? What is their tangential speed? Do you remember that phrasing from first semester? There was discussion of tangential speed, and each one of these people has a different tangential speed because they're making different circles in the same amount of time. Do you remember how to do this? I could remind you, and it's not hard, to go from tangential speed to angular speed and back. Just involves multiplying by the radius. But be careful. This only works when this is in radians. It only works when that value is in radians. If that value is not in radians, it doesn't work. Do you need a refresher on how to convert from rotations to radians? Or do you have that handled? Be honest. If you say you've got it handled, I'll just treat you like you know how to do it. Do I need to help? Okay. I will remind you that I use unit multipliers. So we have 1 rotation every 4 seconds. I want to convert that into radians. So I'll use a unit multiplier. Remember, to use a unit multiplier, you want to put the thing you're trying to cancel on the opposite side of the line. I want to cancel rotations, and I want to be left in radians. I have to remind myself what the conversion fact is. For every 1 rotation, there are 2 pi radians. I always use unit multipliers. I try not to say, am I supposed to divide or multiply by 2 pi? Because that always screws you up. So if you use a unit multiplier and just write it out, you generally will not get this wrong. But if you try to just think in your head of, am I supposed to divide or multiply by 2 pi, you will probably get it wrong some percentage of the time. So just write it out. It doesn't take long. And you'll always ensure you're doing it correctly. So it gives me half a pi, right? Or, and we should probably get a decimal here. I have 1.57 radians per second. So now doing this problem easy. The tangential velocity will simply be 1.57 times either 1 meter, 2 meters, or 3 meters, depending on which person you're talking about. Good so far? Going to add to this. So this will be 1.57 meters per second. This is going to be 3.14 meters per second. And 4.71 meters per second. So while the ride was spinning up, this person right here, they were experiencing a tangential acceleration, right? Because they had a linear velocity of 0, and then after a while, they had a linear velocity of 4.71 meters per second. So they must have had a linear acceleration, something that changed their linear speed. So the first thing I want you to know is that this is not just for velocity. You can apply this to all of your angular values. So if you want to find a linear displacement and you have an angular displacement, this works. If you want to find any of your tangential values, this works. However, always has to be in radians. So if you want to find this person's tangential acceleration, you have a lot of ways you could do it. Like, you know, they go from 0 to 4.71 meters per second in 10 seconds. You could just use that. Or you have their angular speed in rotations per second squared. You could convert that to radians per second squared and then find out their tangential acceleration that way. You can do it either way you want. You have methods now. Now, I note that I'm going to run out of time here, but I have a whole set of homework that's like just kinematics practice, going back and forth, and all the answers are worked out. Your first page of homework is this. Now,